Thank you. Silence. That was everything I needed. While you are in a silence, while you are observing me and thinking about, probably wondering what is coming out from this guy, why he's not talking anything. He must be frustrated, being nervous. A little bit I might be, but while we are processing the information through our sensory organs, in our brains, the neurons are firing, and from this firing, there emerges magnetic fields. And it's not just me or just some of you, but everyone in this room. While we are sitting in this room, we have been generating a magnetic field, though very, very tiny strength, but in your brain here and there comes up and disappear these magnetic fields constantly. And this was literally filling up the whole space in this lecture theater, although we normally don't recognize that. On top of that, there is a very, very tiny magnetic field coming out from the Earth. And that, again, fills up the whole space here. And it's not just us, here or now. It has been everywhere, and every now and then. So if you look up into the sky, in a distance, there must be stars, and some of the large stars very far away, but they are also generating a magnetic field. So it's not just here and now, but has been filling up the whole universe. These magnetic fields has been with us for a long, long time. So today I'm going to talk about magnetism, and I prepared this talk into 3 parts. In the first part, I will discuss, or I will show you around, or let's navigate through the natural magnetic phenomena, from the smallest to the largest in the universe, and from the tiniest or the weakest magnetic field, like those produced in our brains, to a gigantic magnetic field strength produced by neutron stars. On the way through to neutron stars, we'll see that it's not just us, but also the other animals and other planets are also generating magnetic fields. So we are all part of that. And after that, we will step back and then discuss a little bit of the context of this magnetic phenomena and the progress of science, and also, in a sense, the frontier of magnetic science in these days is. And here I will just slide in my own research areas a little bit. So that's the second part. And thirdly, I want to paint the picture where we are in terms of all the progress that has been made over the last few hundred years by the scientists, and how we benefit out of the curiosity-driven research now, and what should be our sort of responsibility for the future generation. So I admit that the scope is a little bit ambitious. As the subtitle says, from atoms to the universe and how it helps us thrive. I don't think any single person can cover the whole areas. So my purpose today is not really pouring out all the knowledges, but rather I want to share a sense of wonder which I felt while navigating through this magnetic phenomena across the whole scale. So let me start from the first part. As a physicist, we tend to start thinking from the tiniest or the most fundamental ingredients in the universe, and that must be atoms. And of course, atoms are made of nucleus and electrons. The nucleus are again made up with protons and neutrons. And those subatomic particles, or the fundamental particles, they are all sort of tiniest magnets that exist in the universe. In that sense, it may not be a surprise that we observe magnetic phenomena here and there, because fundamentally, all the things are made up of magnetic things, or the small needles. As we start this talk by introducing this neuron firing and the magnetic field being generated, when we perceive the things from our external world, and of course I'm not an expert of this phenomena at all, but what I know as a physicist, if there is a current, there should be a magnetic field associated with it. So when we transfer information from this point to that point in your nervous systems, there's a potential difference, and then the charged ions flow through. And when a charged particles move around, then it is nothing but the current, electric current. And when there are electric currents, then they are always accompanied with the emergence of magnetic fields. And it's not just happening in our brain, it happens in every part of our bodies. Like our heart beating, muscle contraction, and peripheral nerves, they all respond to the external world, generating tiny, tiny magnetic fields. It would be absurd if it is just us on Earth which are generating magnetic fields. Other animals do too. But some of these animals are even smarter than us in a sense that they can exploit the magnetic field that is generated by the Earth, and they can navigate through. A sea turtle can come back to where they have born after diving into the sea, traveling along 10,000 kilometers. After a year, they just come back to exactly the same location. How is that possible? And it's not just the sea turtles. There are birds, insects, butterflies. It looks like these animals somehow read the map of magnetic field of the Earth. They know how to go. We don't see this magnetic field. We don't have that map in our hands, but they do. There is a robin here. It's a European robin. It's not UK robin because the UK robin doesn't migrate. They just so love the UK and stay here with us. But these European robins quite often visit the UK, not the other way around, by traveling thousands of kilometers. So we are all familiar with the idea, the concept that the Earth is magnetic. And often it is considered as a big, gigantic magnet. And the truth is that it's nothing like a big magnet is hidden at the core of the Earth, but it's rather dynamic. Inside the Earth, at the outer core, there are molten ions, and then there are convection and motion of these charged particles generate a magnetic field, and we experience that as a tiny Earth magnetic field that is easily detected by this magnetic compass. Funny thing is that because this is a dynamic phenomena, sometimes they do some weird things, like the reversal of the polarity of the Earth. So on average, like every 300,000 years, there is a reversal of the magnetic polarity, meaning that your magnetic north becomes a magnetic south, and magnetic south becomes magnetic north. And of course, this would cause a lot of problems for certain animals. The last one has happened 780,000 years ago. So someone might be worried that next morning we see a different world. But fortunately, this whole process of magnetic reversal is a geological event, and it takes hundreds to thousands of years. So you don't have to worry and sleep tight tonight.
Sorry, did you say hundreds of thousands of years for it to flip?
Yeah, so it happens really slowly.
Yeah.
And as far as we can tell, there's no evidence that this is happening now.
And how long, sorry, was the period of the flipping?
Flipping, it actually varies. So there is no set time period.
So it's 100,000 years?
Yeah, 100,000 years. And we can't retrieve all the information in the whole history of the Earth. It is just a few hundred millions of years from the geological evidences. And so how do we find this? There has been a magnetic reversal. If you go into the mid-ocean, there is a ridge where the two plates are meeting together. And there, the Earth crust is constantly recreated, starting from the magma. And this magma solidifies, and then they push away and creating the new Earth crust. And while this magnetic field reversal polarity is happening, this is recorded on the rocks that has been just created. So it's like, if you are mature enough, you will recognize there has been a record tape, magnetic record tape, and this is not much different from that. It's recording the history of the Earth on the scale of thousands and hundred thousands of years. And that gave us an evidence that the Earth, all these continents, are sitting above the crust, which is kind of a section by what we call a tectonic. And if you see, so this color map is representing the age of these areas, and you can see the red colors following this, the boundaries between the continent. And because they are young, because they have been recreated from the magma. And this provides us an evidence that this crust is not static, has been sitting there forever, but it has been actually moving around. So this Earth magnetic field is a kind of a fossil or the history book of the Earth on the scale of millions of years. Earth magnetic field also saves life. It protects us. It protects us from a very harmful solar winds or the cosmic rays. Sun itself generates a lot of magnetic fields, and they radiate the plasma which has been magnetized. And because the Earth is magnetic, Sun is magnetic, it's not surprising the other planets are also magnetic, like the Saturn. And if nearly all the members of our solar systems are magnetic, we can easily imagine that all the astrophysical objects would be magnetic as well, if not all. And indeed, one of the most intense magnetic field source in the universe is what is called the neutron star. And they generate a magnetic field which is 1 trillion times stronger than the Earth magnetic field. If such many astrophysical objects are magnetic, then what happens in between? We know that there exists an empty space, a vast empty space between the stars, between the galaxies, and between the galaxy clusters. They're really, really empty. So if you compare with a vacuum cleaner, it's like billions of times emptier than the vacuum that your vacuum cleaner can provide. If you're in this cosmic void, you travel along one direction, then you will meet one particle every few kilometers. Imagine that we ourselves are made of 10 to 22, 23 number of particles. This is really, really empty space. But from the magnetic point of view, it's not empty at all. Actually, it's totally fulfilled by the magnetic field. Here, what this column represents is the density of a dust while looking at certain parts of our galaxy. But all these texture represent the field direction, the magnetic field direction. They are not strong magnetic field. They are a billion times weaker than the Earth's magnetic field. So really, really weak. But given the scale of the space that they are occupying, this is really a lot. So already this is the end of the first part. In this first part, we have navigated through the magnetic phenomena that we may encounter or that I can introduce you at all scales, starting from the tiniest in the universe to the most intense astrophysical objects, from the very weak neural activities to extremely strong astrophysical activities like neutron stars, and also from the simplest fundamental ingredients of the universe to complex systems like biological systems. So magnetism literally permeates through everything, and I think this is a great insight. And it permeates through everything, everywhere, and every now and then. That is the sort of the first take-home message from this lecture. And then now I want to step back to see how we begin to understand these things, how we begin to explore this magnetic phenomena in nature. And that is partly related to my own research. So I will also introduce a little bit of my research, which is called quantum magnetism. After discussing all these fancy biological brain, atoms, universe, neutron stars, we suddenly look into a horseshoe magnet. And you may think this is a bit boring, but this is where all the things related to magnetism has begun. The guy here, whose name is Gilbert, has been a physician to the Queen Elizabeth I. But he was also a scientist. He's not as famous as Galileo Galilei, but by the historians of science, he is considered one of those founders of modern science. Before his time, people believed that, actually they didn't have a clear idea why a compass needle is pointing to certain directions, to the North Pole. And I think he's not the only one, but he believed that the Earth itself is a gigantic magnet. But the difference he had made is he did an experiment. He made a model. He made a big sphere out of low stones. So this big stone is a magnet. And then he brings these needles and then move around this sphere. And of course, we know that this compass needle will point along the North Pole. That is not a surprise. But what he has found is that when this needle is at the equator, it is just pointing along vertically. But as you move along towards the North Pole, then this magnetic needle actually deflects and pointing downward, as represented by this figure on the right. So there was a hypothesis, and then there was a design of the experiment, and the verification. So that is why this is considered as the beginning of the modern science. And as a person who is doing research in the field of magnetism, I'm quite proud that the magnetism has been the beginning of the modern science. I note that some of you may remember this banknote, which has been used between 1991 to 1999. Michael Faraday on this 20-pound banknote, and he's giving a lecture in this famous Royal Institution. This is just a side note, but before Michael Faraday, it was Shakespeare on the 20-pound note. So that gives us an impression how significant this figure in the history. This looks like a child play. We all know, we all understand what it means. There is a magnet, and then there's an ion filling, and then they just distribute themselves following certain lines. But it was Michael Faraday who did first systematic study of this by bringing different magnets, arrange them, and then carefully investigate the distribution of those lines, and came up with a concept of a field which underlies all the modern physics. So what he proposed was that this can be only explained by the idea that at every point, at every time, you can assign a strength and direction of certain force. So before Faraday, before he visualized the magnetic force by this simple experiment, it was not clear how these magnetic forces are mediated from here to there, why these two objects are attracting or repelling each other. But here he has introduced concept of fields, a field of force, and then try to explain this. These two people are one of the most famous couples in the history of science, Marie Curie and Pierre Curie. And Pierre Curie was also a famous and distinguished scientist, although he is often overshadowed by the fame of Marie Curie. What he has contributed to this field of magnetism is, again, bring the fridge magnet or the lodestones, and then he did an experiment. He heated up the magnets and found that the magnetism disappeared. So he traced the temperature evolution of magnetism in a material and found that there is a sharp transition which distinguishes between the same material being either non-magnetic or magnetic. And this supports the idea that possibly when there is a magnet or magnetic materials, if you go into the tiniest scale, there will be atoms or electrons that are pointing along the same direction, where each of these could be considered as a tiniest magnet. And the explanation that follows is that if these tiniest magnets in the universe are all aligning with each other because they are favoring their neighbors pointing along the same direction. So if one is pointing in this way, the second one, while fluctuating, they recognize the first one and point along the same direction, and the one next to each other. So the explanation it provides is that at low temperature, because there is no thermal agitations, they will just be able to communicate with each other well, and then they decide, okay, let's point along this direction, all follows. if they are at a high temperature, because of these thermal fluctuations, they can't really communicate each other very well because of this noise of the thermal vibrations. So they are non-magnetic. So over a few hundred years, that was the kind of a progress of our understanding of magnetic phenomena. And our understanding of magnetic phenomena really comes from the magnetic materials, which is not really different from the fridge magnets. And I admit that this is not as exotic as astrophysics or particle physics. But don't expect me to do the research on these kind of things. This is no offense to my geologist colleague who is looking into these minerals. But this is something I studied. This is a material, well, I mean, not this solenoid, but these beautiful pink crystals. You see that they are transparent, they are shiny, pink colored. This is the sort of magnets that I'm studying. And this is something one can synthesize in a lab in just a day. These are examples from my colleagues. I would appreciate the difference in their shapes and colors. So personally, it's not boring at all looking into these beautiful crystals. It's actually quite fun. What colors they might be in our next synthesis. And these crystals, as much as they look different, as much as they appear different, they all carry different stories. And that is what I am actually interested in. In these beautiful crystals, different dimensionality, different geometry, and different worlds or universe. So in some of these materials, the atoms are arranged predominantly along one direction. And because the distance between these one-dimensional objects are too far away, they can't really communicate with each other. And you can consider this as a kind of mere collection of one-dimensional world. In some of these crystals, they are arranged predominantly in two dimensions, and because the distance between these two layers are too far away, again, they can't really communicate well. So even though they may appear three-dimensional, inside these materials, if you just look into the problem, look into this material at atomic scale, they may realize one-dimensional universe and two-dimensional universe. And one may say that, okay, you're a little bit overselling. Why do you call it a universe? I don't know whether you are familiar with this book. This is a fantastic book written at the beginning of the 20th century by a British headmaster. Flatland. It's a story about a world, two-dimensional world, by a character called a square. And it explains, or it explores the issue, how difficult it is to understand those living in different dimensions. The communication between different dimensionality is literally not possible. And the example is drawn here, so while this square is living in a two-dimensional, they were visited by a sphere, which used to live in a three-dimensional world. And this three-dimensional sphere wants to explain what it means by being a sphere. But those characters living in two dimensions really couldn't understand, but this helped. They observed that the circle projected onto this two-dimensional sphere is changing their radius as it moves up and down. And this gives us a kind of a hint how to approach understanding the characters living in different... Anyway, this is not really related to this talk, but I just wanted to introduce this fascinating book for you. Why I call it a different universe? Because something funny and not easy to understand happens in 1 dimension or 2 dimension. If you make a crystal which realizes these 1-dimensional chains in these crystals, the funny thing is that the electron, which is a fundamental particle of the universe, split into 2. The electron is the tiniest magnet at the same time as it carries an electrical charge. But if you just confine these electrons and let there be many electrons move around, they suddenly fractionalize into charge degrees of freedom and magnetic degrees of freedom. So the identity of an electron has been lost. And instead of having just 1 electron as a character, has both charge and magnetism, now their characters are split into 2. And this doesn't make sense if you just consider 1 electron in 3-dimensional space, because an electron is a fundamental particle. Now, if you bring these electrons to 2-dimensional universe and then apply an intense magnetic field, these electrons, which carries 1 electrical charge, now split into 3, as if the fundamental units of a charge has been redefined. And again, this can't happen in 3-dimensional world when you deal with a single electron. This is a manifestation of interaction of many electrons in 2 dimensions. So in that sense, I kind of insist that by studying these materials, seemingly beautiful, aesthetically pleasing crystals, I'm actually looking into a different universe. And if you synthesize new materials, it's something like creating a new universe, and you would never know what exotic things may happen, like this fractionalization of fundamental particles. And eventually, what I want to do in my own research area is synthesize new materials and then try to understand what exotic things are happening and potentially creating a new states of matter that might have not existed in the universe, in the history of the universe, and nowhere else in the universe. For instance, we have just seen how we understand the magnetism of a magnet material. At high temperature, they are all fluctuating randomly. As you cool down, the communication builds up, they point along the same direction. But for certain materials, it turned out, at least theoretically, they can't really settle down. However, you cool down the materials. So, in my mind, if you just cool the things to absolute 0 temperature, for instance, where you can't imagine thermal fluctuations, then everything is so quiet and calm, and they need to discuss, they need to communicate with each other. And they do, but still, they do not want to develop this kind of order. But instead, they develop some sort of intimate relationship between each other. So these, although they look like pointing into a random direction, they are actually highly correlated and highly coherent, and they know exactly what they are doing. Because at 0 temperature, there is no random thermal fluctuations. And this, in the previous slides, is perfectly okay if you don't follow this. It's just, as I have highlighted in the beginning, this is sort of a frontier of magnetism research. And we soon move out from this topic. That guy in a red shirt is me 20 years ago when I was a PhD student. I was doing experiment in Kyoto University at the time, and you can see some gigantic equipment on the left-hand side. And that was just to provide the right condition to explore this phenomenon on the left. I was looking for a material which does not order or which does not communicate in a common sense, at the lowest temperature. So the equipment that is shown in this photo allows you to cool down the material to a temperature which is 100 times colder than the outer space. And one can imagine how expensive this kind of a fundamental science would be following the curiosity. But all these fantastic array of phenomena that we discovered in nature in terms of magnetism, the research activities and our understanding built on a few historical milestones over a few hundred years. So Gilbert has published his paper or his book on magnetism in 1600. And after 200 years, Michael Faraday. And at the beginning of 20th century, Pierre Curie. So it's more than 400 years since Gilbert. And I can assure that all of them, they just follow their curiosity. Now, in the third part of the talk, I want to dive into the implication or the outcome or the impact of those curiosity-driven magnetic research in our world. And that relates to the subtitle, how it helps us to thrive. Again, we began with the brain activities and this tiniest strength of magnetic field that the brain generates. And one should wonder, how do we know if it is that tiny? Now we have tools, more than a single tool, to prove the brain activities. And we can locate where the activities take place in what time scale. And this certainly helps us to improve our health and well-being conditions. So in this third part, what I want to emphasize is how this magnetism over the last that has been developed over the last 400 years is shaping our society currently and help us to shape the next generation through health and well-being and environment and sustainability and prosperity and economy. Again, that is a bit bold and ambitious, but let me just quickly browse through the examples. And this is another well-established, well-known examples. You visit the hospitals everywhere. In the hospital, you can find MRI machine, which is a magnetic resonance imaging techniques, saving hundreds and thousands of people every year. And this magnetic resonance imaging machine builds on a very specialized magnetic material called a superconductor. And this superconductor allows us to generate a very precise and homogeneous magnetic field, which is hundreds of thousands times stronger than the Earth's magnetic field. And it's not just to diagnose the disease of in the human bodies, but we can also design the drugs thanks to the technologies built on the magnetism. What is shown here is the equipment that is located on the other side of the campus, which is called nuclear magnetic resonance. So using this equipment, you are looking into the nucleus, how this magnetism of the nucleus changes. And this allows to look into the molecules at an atomic scales and help us to design the drugs, help us to understand better the proteins and their dynamics. We can encounter these wind turbines anywhere in the UK, and they are generating the electricity because there are magnets. In each of them, a half ton of the neodymium magnetic materials are there to generate the clean energy. In terms of environment and sustainability, we can't omit the electric vehicles. Instead of the engines, we have now motors, and motor again builds on the magnetic materials. And actually, it all started from the Faraday's toy-like research into the magnets, because Michael Faraday has actually has actually laid the foundation for the electric generator and motor. Hard disk drive is now retiring from the laptops, but still in wide use. And again, this builds on the magnetic materials. But it's not just the current technologies. If we look into the future with quantum technologies, many of the quantum computers build on the cryogenic techniques that uses the superconducting magnets and the superconducting quantum bits. So this is just a few of the examples that I can find how the magnetic materials shapes our culture, shapes our society. Before concluding, I want to draw your attention to a slightly different aspects of doing magnetic research. Because I believe that magnetism is not just about the science, curiosity, or the civilization. It is actually more than that. This is one example. This is, I don't know, she's now wearing a headphone, holding a smartphone, I guess, and charging the electric vehicles. And how much do you recognize in this picture magnets are used? In just one example of a smartphone, you have a microphone, which uses magnetic materials. A speaker, again, uses magnetic materials. And autofocusing, so you have a high contrast and sharp images of the photos, is made possible with this autofocusing, which again uses magnetic materials. And to charge your iPhone in a convenient way. And also the haptic motions. And all this immersive experience is empowered by using a strong magnet called a neodymium magnet. So when I was doing experiment in the basement for cooling the materials down to very cold temperatures, 20 years ago, there was no smartphone. Some of you may remember the period where we didn't have this smartphone. And imagine how much the culture has been changed with the advent of this smartphone. And I assure you, a significant part of that owes to the advanced materials like these neodymium magnets. And we mentioned these electric vehicles, wind turbine for clean energy, sustainability. They all use a very strong magnet based on neodymium, like the smartphone. There's a problem. It leaves a significant footprint. It literally destroys part of our home, the Earth. To get this neodymium, you have to mine. And during these mining processes and purification processes, a lot of chemicals, toxic chemicals are used, and that pollutes the areas. So the magnetism in the modern days is not just about the magnetic materials themselves, but it involves some geopolitical issues and societal issues can you give up using the electric vehicles because you are worried about the environmental impact? That is something we need to kind of discuss among ourselves. Because one may think, okay, let's just recycle them, right? If it is generating that much toxic environmental footprint, why don't we just recycle them? And actually, at the University of Birmingham, we have a very large center focused on these activities. But you can imagine that the car companies probably doesn't want to share the secrets of their motors. So if you get a motor or the battery from the electric vehicles and you want to recycle them, then every motor have different designs and different materials, and you need to dig into what are they made of to be able to recycle them. But it's not easy. So this calls for the societal attention to the recyclability of these precious materials or the strategic elements by pushing the politicians to set up regulations that when you introduce a new model of the electric vehicles, you have to also guarantee how you will recycle these precious materials. But just for this lecture, I think finishing these lectures with all these negative things is not really ideal. This is something I want to paint. That magnetism is nothing. Magnetism is actually empowering our society by creating a new culture and helping people to live a decent life. I think it's somehow following the sort of a philosophy or the vision of Francis Bacon, the UK philosopher. Often he's criticized that he was kind of against the pure science, but still he believed that science should better a human condition. And although the motivation which has led us over the last 400 or 500 years is driven by pure curiosity, the outcome is really, as you see, significant. And certainly I believe that the human condition has been bettered by the magnetism research. So you may think, I believe you will not, but some of the people may think that spending a fortune to fundamental research might be a waste of money, but it's not the investment for us now, but it is the investment for the future generation. Maybe not in 30 years, maybe not in 100 years, but probably in 200 or 300 years later. And I will close this talk by now. Thank you very much for your attention.